All right, thank you all again for joining us today. I am Glenn Miller, a sales engineer with ACI, and presenting today is Chris Burrows, who is the product manager at Price Industries' Stratified Air Systems team. Today, Chris will be presenting on solutions for today's IAQ challenges for Office, K through 12, and other applications. And without further ado, Chris Burrows.
All right. Well, thank you, Glenn, and thanks everyone who's joining us this morning on this topic. You know, we wanted to focus on, like Glenn was saying, you know, how do we overcome the current challenges that we're seeing in a couple applications, office and education specifically. We feel that there's been a large adoption and it kind of has been very commonly used in, you know, large spaces, implementing stratified air systems. The taller the space gets, the more you can stratify and really squeeze energy savings from, you know, just conditioning the occupied zone. But just want to take some time today to talk about, again, office and education and how these systems can be applied and really provide benefit to everyone involved throughout the process in terms of design, overcoming challenges with indoor air quality, the owner's perspective or developer's perspective with the offices, in terms of, you know, how do you get people back in and safely, and what kind of options do we have for designing for the future, taking into account you know, indoor air quality, you know, and energy savings, but also keeping it first cost competitive with these other systems. So we've got a couple options that we want to talk through. Again, this is a very abbreviated version, as Glenn was mentioning, so feel free to get in touch with us on a kind of a follow-up or further discussion. So just 3 items or sort of sections for today. Start out with system review and get into the benefits as it relates to how these systems operate, as well as, you know, the workplace and education, what types of systems we would suggest here. So real quick, always like to talk about the differences. You know, in a traditional system where you're inducing room air, you know, you're injecting the air typically along the ceiling or just along the at high velocity above the occupied zone. And the intent is to uniformly mix both temperature and contaminants throughout the space through dilution. So that's kind of mixing in a nutshell, or at least the concept. And the intent is that you've got higher static. You're pushing the air with the fan static through these diffusers at high velocity to kind of mix all that throughout and induce room air upwards towards that diffuser. In displacement, what we have is, you know, whether it's displacement or underfloor air, as we'll refer to another system, in that sense, you're supplying from low level, either in the wall at near the floor, or even in the case of an underfloor air system, directly from the floor. And the idea is that you're supplying the air at a slightly elevated temperature. Anywhere from 62 to 68 degrees is fairly common between the two systems. And it's a single pass system. So we'll get right into this video. Hopefully it's coming through without too much lag and coming through at good quality. So here's in our tech center, our demonstration center in Atlanta, where I'm located. You can see the air's coming out around 40 feet per minute, nominal across the face. And it's seeking out the various thermal plumes. In the case here, we've got our thermal mannequins, which represents a typical sensible load of an occupant or student or adult. And what you can see is, once this comes around to play again, you can see the air is moving very slow, even across the ankle region, and much slower than what it is across our normal thermal plume velocity. So we're naturally used to feeling quicker velocities across our body from the thermal plume, as compared to the velocity across the floor plate, you know, a foot or two away from the diffuser. So this really creates a comfortable environment. It's self-balancing. You've got the air seeking out each occupant based on how much load they're giving off to the space, or heat they're generating. But also it's, again, that single pass system. You can see the fresh, cool air is being brought throughout the space, kind of filling like a bathtub, if you will, and moving upwards, you know, so you've got CO2 in the case of breathing, sneezing or various contaminants that would be carried through, say, breathing from one occupant to another. That's going to be brought upwards throughout the space through these thermal plumes and, in general, the upward movement of air throughout the space. So that could be a significant benefit and has been a significant benefit in studies that have looked at indoor air quality or air changes effectiveness in these various applications with these systems. So on that note, there's a study done a couple years ago that looked at air change effectiveness, which is essentially how quickly does the air get from the supply point to the breathing zone in comparison to the supply point to the return. In a mixed system, you would expect that to be nearly equal, and it's just the ratio of those two, of those time constants. Unity, or 1.0, would be expected of a mixed system, but with UFAD and displacement, you can see that the average is about 30% better throughout the floor. But when you look at the local max, which is typically where the thermal plumes or the occupants are, where all that air change is happening, you've got a significantly high level of air changes in the space. A little bit higher with underfloor than in-wall displacement, again, because your ground floor, your supply points are very close to the occupants, meaning that you can put them in the floor, hide them underneath desks. So huge bump in air quality associated with these systems. Obviously, that leads to a number of opportunities for, well building standard. There's a lot of various features that underfloor and displacement can help earn towards that effort. And even in the case of, surveys or what owners are saying about their buildings using underfloor air, one large developer is a pretty big proponent of underfloor air systems, noting that they've had a significant reduction in hot-cold complaints, even more so over the BOMA standards, which is why they continue to use it. In terms of operating cost, there is a deduct associated with fan horsepower, because you're supplying air at low velocity into the space. Usually 0.05 inches or less is the typical pressure drop across these diffusers, or what's needed to kind of move the air through the diffusers themselves. Less expensive to cool, so now we're dealing with 65-degree air on average instead of 55 degrees. So specifically for your climate, if you design a lot in state, that's going to be a significant amount of hours throughout the year that you can free cool, which can be obviously 100% outside air. It can be even further improvement in air quality instead of a portion of the total air being just fresh air. So you'll see a pretty significant pickup there. So there's a lot of different options in terms of the benefits there. There's been a couple of projects that we highlight that have really seen a lot of energy savings. This one was actually a secondary education, Upper Iowa University, that noted 67% energy savings by using underfloor air system with a radiant product, and they were able to recoup their initial cost. Again, this is kind of a more premium system than your conventional UFAD, but recoup the cost of the capital spend in 3.5 years, which was quite significant. Here's what I was mentioning on, again, lowering operating costs throughout the years using free cooling. You can see that out of most of the areas in the country, there's a lot of opportunity in the state of Washington. Very similar, I think, around 2,800 hours between 7 a.m. and 5 p.m. In Portland and throughout that area in Oregon. One thing to note, this was done looking at anything at 55-degree dew point or below, just taking into account the hours where it's too humid in the air outside. So again, we see this a lot of times, again, in very, very tall spaces, either libraries, performing arts centers, auditoriums. A lot of that is really driven because you can architecturally hide it underneath the seating and supply air that way. And again, directly supplying the air into the breathing zone it makes for a very superior indoor air quality system. But also it's very low static, low airspeed, which helps with the noise generated from these types of diffusers being pretty minimal and usually below net background noise levels, which are helpful for this space. All right, so getting into workplaces. So again, this is a very important topic nowadays as everyone is continually adjusting. They're kind of taking a step back and reorganizing furniture and layouts, putting up obstacles in different sort of scenarios and strategies. So there's really no better system that can achieve the type of flexibility underfloor air involves. You usually have minimal, if any, ductwork depending on the core to tenant space layout proportion. Usually you don't need any ductwork underneath the floor, definitely not directly to the diffusers. So, easily removing the carpet and rotating or moving the round floor around to move the supply air point instead of having to get up and cut into diffusers and sheet metal and move those things around and possibly, reorder new diffusers. This is a really flexible system, and the ability to reuse existing, wiring and power, as well as the HVAC is really helpful in saving costs as the business continues to evolve. This is another one here. You can see that, with underfloor air, there is a sort of a misconception, or at least the idea that, with raised access floor, you have to just add 12 inches to your facade height per floor. But when you look at, either exposed ceilings or different techniques, even if you have a short return air plenum above, you're really dealing with just 12 inches of raised access floor height. And then whatever, if there is a ceiling, whatever that might add to it, whether it's 12 inches or so, you're going to end up being around the same overall interstitial space, if not a little lower, which is what a lot of clients have seen in using these systems. You also can have, again, with the exposed ceilings, more natural daylighting, which can be really helpful in terms of the indoor environmental quality. So one thing to note, just want to bring up here, especially in the Pacific Northwest, is that if you've got a mass timber project, underfloor air is really helpful in augmenting or highlighting those architectural features and not covering up the ceiling with ductwork or hard-lit ceiling to get air out from the ceiling to condition below. Instead, you can just, again, kind of hide that underneath the raised access floor and provide an exposed ceiling. So we hear a lot of architects, really enjoying us bringing this up, and they, a lot of them were not aware that this was kind of a good synergy of the two types of mass timber and then the underfloor air system. So just want to put it out there that working on several projects throughout the country that are using this type of technique. This one here we supplied several years ago here locally. So an owner would go with a raised access floor for putting, power and data underneath the floor, and then basically increasing the floor a couple inches up to 12 inches. We used to see 16 inches. Now we're seeing it lower and lower, 10 and 12 inches in height, and really optimizing the amount of interstitial space down to that level. You really could see a lot of facade savings. A lot of times you might actually just keep that additional occupied space and just have higher ceiling heights. But for a mid to high rise, you could see significant facade savings if you have an exposed ceiling. This quote here is from, again, the same developer we were talking about earlier, where they're quoting out a net savings on the mechanical spend of $5 to $7 per rentable square foot, just because you don't have any moving parts or fans all throughout the occupied space, no ductwork and things like that. So again, really helpful. Those things combined along with reduced cabling links and making all that plug and play really helps kind of shave on the first cost that's burdened by the owner. So we just want to show a quick video of the flexibility of the underfloor air system. This video is going to be posted online here, but it's a brand new video, just kind of showing the various flexibility, modularity elements of the space. So we're going to go up and kind of show, just for the sake of time, kind of quickly skim through this. So we've got an elevated view of an open office, and what's going to happen is the owner's got a requirement to add a conference room and 3 individual offices along the perimeter. So we're going to zoom in and kind of show the perimeter office, conference room on the corner, and essentially utilizing the same power and zone distribution boxes that we're going to move to be underneath the conference room table and replug in the data and the power, which again are all using modular power connections. So, local code permitting, this could really be done by, facilities and the maintenance without contracting anybody in, and ultimately saving on cost. And then we're going to replug in or unplug and plug into the power control module, what's going to control the perimeter zone here. And then we're removing the manual diffusers that were in the open office and plugging in automated baskets, utilizing existing diffuser face and ring. So again, all that's plug and play back to the power and control module. Usually you're dealing with, floating structure walls that can be just brought in over top the floor. And then we'll move in kind of put together the private offices. So again, as you start to, if you're hearing clients, like we're hearing people kind of ask, what can I consider for my new construction? I've got a 100,000 square foot space that is in design, and what options do I have to secure, the future and kind of create these modular spaces, but also indoor air quality, and how do we improve that to make the employees feel safe? This is a really good option to consider and put in the toolkit. All right, so again, you might don't have much time to spend on the layout and getting into the zone details. Again, we can talk about that at a later time if interested. Here's an example of the decoupled version of the cooling system for this underfloor air, where we've got air towers at each corner of the core, and they're discharging downwards and pressurizing the underfloor plenum. So the outside air is being distributed and then ducted either to the top or just supplying into the mechanical rooms that are out of the core and into the tenant space. And then that's handling your cooling, your sensible cooling through the cooling coil and conditioning that the underfloor air plenum. Then we've got manual round floors located throughout. Again, very simple, elegant design, pretty much the same diffuser and face that's placed evenly throughout, giving occupants control of their thermal, their air supply volume. And then here, there has been an evolution in underfloor air systems, moving from, fan-powered terminals and putting fans, at least a large amount of fans underneath the floor, and shifting to these natural convective troughs, where each of the active sections underneath the floor grill utilize space return air that falls down into this plenum and then heats up in the case of heating. For cooling, you can have a VAV damper that just modulates to condition the perimeter in cooling. So again, these work quite nicely with condensing boilers. 100 to 140 degrees is pretty typical of incoming water temperature to these troughs to handle your 750 BTUs to 1 MBH per foot along the perimeter. All right, so getting into education, just real quickly want to talk about the different methods in which displacement, again, shifting from underfloor air to a in-wall displacement approach. Here's the most common way that we see it installed, where you've got kind of this drywall channel or chase. We've got a round duct coming down to the top of a plenum, and then you've got the displacement diffuser face installed into that plenum. So basically, there's a lot of ways in which you can supply displacement into a classroom. If you've got a school district that's used to furniture, a certain set number of furniture in the space, you can actually integrate it into the kicker and pressurize that. So that way you're not giving up any more usable program area in the classroom. And then there's ceiling displacement. This might be a good retrofit option, as there are a lot of schools out there already built and probably looking for, what are the options I have to maybe do a retrofit kit or change out an existing overhead system and convert that to displacement. So we're working on a couple brochures specific to that we'll be releasing soon, but certainly the product exists that can make that easy for a switch out. And then heavy gauge, options for gymnasiums or other high traffic areas where you might have obstacles being thrown up against them, in that sort of application. So this is not an old system, a new system being applied in schools. It's been around for a while and being applied in the wild. In fact, for quite a while in your area, in the Pacific Northwest, in schools. EPA, CHIPS, Collaborative for High Performance Schools, actually suggest the use of displacement type of a system in the classroom. And we could provide all the references for the studies or information that they put out there on designing classrooms with healthy IAQ. So one thing to note is there's no moving parts or filters to change with an all-air displacement system, or even a sensible cooling-only chilled beam that provides a displacement pattern in it as well. So really just minimizing your in-space maintenance for the classroom, any disruptions or anything like that, loud fans kicking on and off, and those sort of things. So very simple approach. There are a lot of studies that look at displacement in classrooms and what's the effect of using displacement in terms of asthmatic, flu-like symptoms, respiratory viruses and things like that. And there's quite a bit out there that look at the improvements with displacement. The first one there compares a run of displacement classrooms in the same school as classrooms across the hall with mixed air ceiling supply, and they noted a significantly lower peak CO2 level in the space, naturally due to that smoke demonstration video that we had shown, where it's moving all those contaminants out of the breathing zone. This was a CFD study that we did for the classroom environment. Is one school up in Canada that looked at comparing traditional with displacement and what the CO2 levels, how that's kind of being moved throughout the space. You can see that those thermal plumes are kind of doing the job and moving the higher parts per million CO2 exhausted from the students up immediately out of the breathing zone. So this can be a significant impact in terms of not only keeping the kids healthy and the teachers healthier, but keeping them in class and in school, and reduce that absenteeism. So again, because of that, again, going back to that smoke video, it fills the space out evenly. It's not supplying from one side of the room and trying to uniformly mix and churn up the space. Because it operates on an individual thermal plume level, you really get that 90% plus occupant satisfaction with this system, because of just how it inherently is going to seek out based on how much heat is being given off by an occupant, and kind of balance out that way. Okay, so last note, just want to mention in terms of first cost, there's actually a lot of studies looking at first cost in the Pacific Northwest with displacement, showing that your mechanical spend is actually the same as a traditional system. But there's also the opportunity, annually to receive funding, based on attendance rates and however it might be measured locally for the state that you work in. This usually averages out to about $8,000 per student, whenever that's measured throughout the year, which can be pretty significant, especially as you start to talk about a couple hundred extra, kids back in the class for a district. That could be very significant annual increase to the budget. Okay, well, I know that was a lot of content. Again, I wanted to try and keep this short and succinct. To just summarize, here are a couple of the points that we talked about. hopefully this was helpful and very relevant for the discussions that you might be hearing out in the industry today. So I think with that, I'll pass it back to Glenn.
Yeah, thanks, Chris. And it looks like we've had a few questions come in over the presentation, so I'll just start working through those and yeah, see what we got. So the first question from Vernon's, what quantity of air is delivered to the space in terms of CFM per square foot?
Yeah, so that I know there's been a couple of kind of methods for conditioning the schools in the area. There's still some application of ventilation only approach where that might be, less than a half a CFM per square foot. I think a lot of the schools are going to cooling and ventilation in your area. Not to get too specific, but usually you're at, even though you have 65-degree supplier temperature of air delivery, with displacement, you don't need double the amount of CFM, which might not be what that gentleman's getting at, but what ends up happening is because you're conditioning just the occupied zone, you actually end up about what we've seen is about the same CFM per square foot needed, a CFM or less than CFM per square foot, even with that elevated supplier temperature. Yeah, so hopefully that kind of answers that question.
Okay, great. And then the next question, if you want to actually hop back to that hours of free cooling slide.
Sure.
John Taylor asks, what was indicated by the percent on the slide that had the map of the states where the number of hours available for free cooling were?
Excellent question. So thanks for asking that. So that is the percentage increase by going to displacement ventilation over a 55 degrees Fahrenheit air delivery system. So roughly that 3130 is the number of hours of displacement free cooling, and then that's a 50% increase over what you would have with a traditional system.
Right. Okay, moving on to the next question, which does get a little more detailed, so probably something that would be covered in a longer presentation, but good to bring up. When in the presentation are the challenges of underfloor air distribution discussed, i.e. sealing all penetrations, testing sections as progress through floor plates, etc.?
I'm not sure. I'm not sure I quite follow. In terms of they're definitely
for the challenges and kind of higher level detail is what I'm thinking. Vern, feel free to follow up with another question if there was something specific.
Yeah, certainly, Glenn. There is much more information and design into an underfloor air system. There's especially just the sealing up of the plenum, and making sure that sealed up is we've got a lot of webinars even online that actually talk about just plenum integrity and how do you manage that and ensure that it's you get a successful project. But yeah, definitely afterwards, certainly a longer type of discussion.
Yep, for sure. Okay, great. And then the last question, another good one. Are you advocating using the displacement air to add heat to the space?
Yeah, so that I wouldn't necessarily go that approach unless you're in a more milder climate in terms of the heating requirement throughout the year. Typically for cooler climates, you have even for a classroom, you might have some fin tube, either hydronic or electric, along the perimeter, or a ceiling radiant panel or in-slab heating. Each of the displacement diffusers can come suited with a switchover design, where it can essentially, morning warm up or whenever you might need to kick on the heating, if there's not students in the classroom, you can essentially mix the space, use warmer, elevated temperatures instead of using the low velocity supply portion of the face. But what we've seen is, I think typically fin tube, radiant heating underneath the sort of at the perimeter in your climates, instead of using the low velocity air and heating.
Okay. Okay, and sorry, going back to the ceiling all penetrations, and we had a follow-up that he's looking to for a little clarification on how you can achieve getting the air to where you want it to go, when you take into consideration leakage and whatever else.
Oh, I see. Yeah, so I was mentioning you can really minimize the amount of ductwork with the UFAD system. We're starting to see a lot of this type of design where you've got a vertical discharge unit at each corner of the building, and that way you've really minimized the path or the length in which the air has to travel underneath the floor. In underfloor air systems, you might pick up some thermal gain because below the floor is, your return plenum. That's going to be warmer than your supply, obviously. So that, you will need to design to pick up some of that. But getting the air to within 50 feet of its further distance of travel is really going to help minimize the amount that would happen. Leakage, there is some leakage through the floor air towel, the raised floor system, which is going into the occupied zone, but there's a number of methods in which you can minimize that, especially uncontrolled, undesired leakage that's, through the walls, behind thermostats, and those sort of things. Basically, coordinating and ensuring up front that those are minimized during construction can be done pretty easily to help that. Yeah. Thank you, Glenn. Thanks, everyone.
Yep.